In this work, we present a computational approach for creating zoomorphic shapes. Our approach can turn this ordinary playground into an exciting zoomorphic playground. Zoomorphic shapes are man-made shapes that possess the form or appearance of an animal. Zoomorphism is present in historical designs. Here we show an ancient bull-shaped vessel and a lion cannon. Zoomorphism is also popular in the design of furniture and children's toy. Combining a table and a turtle, we get a turtle table. Combining a merry-go-round and an octopus, we get an octopus merry-go-round. Zoomorphic shapes are non-trivial to create. For example, naively combining the face and mug creates a mug that cannot hold water. Our approach handles this and similar problems automatically. Here's a brief overview of our approach. Given a database of input shapes, our approach first selects a pair of good candidates for creating a zoomorphic shape. Then it deforms the two input shapes to minimize an energy measuring several design objectives. Finally, it removes materials from the two input shapes and takes their union to produce the final output. The input shapes are pre-segmented. To select pairs of shapes to combine, we construct a graph representation of each shape. We then compute the similarity between each pair of shapes by comparing the graphs using a graph kernel. A node kernel compares the similarity between segments, an edge kernel compares the similarity between the edges connecting the segments. Given a pair of shapes from the previous step, there are many different ways to arrange them together, which we refer to as configurations. Our goal is to find a good configuration to create a zoomorphic shape. We introduce a volumetric design restriction to ensure that the zoomorphic shape created by our optimization process will satisfy the design constraints of the base shape. For example, in the design of this insect chair, the volumetric design restriction signals our optimizer to bend the tail away from the sitting area so that the resulting chair remains sittable. In the design of a face mug, the volumetric design restriction keeps the mug hollow so that the resulting shape can hold water. The volumetric design restriction is given by a label associated with the base mesh surface, which the user provides interactively. Here we show our tool for creating a volumetric design restriction. The user wants to reserve a space on the tricycle seat for someone to sit on. The user paints the tricycle surface with the label that creates this space. Here the user wants to ensure that the animal shape does not contact the tricycle wheels. They create a buffer around the wheels. The size of this buffer can be visualized interactively. Our configuration energy considers the animal shape deformation, base shape deformation, registration, visual saliency, and gash. The deformation term ensures that both the base shape and the animal shape are not excessively distorted. The registration term ensures that the shapes are well aligned with each other. Our approach also computes the prominence of the visual salient regions for different viewpoints to ensure that they are preserved in the zoomorphic shape. We also include a gash term to avoid the formation of gashes in the zoomorphic shape. This is determined from the volumetric design restriction. A correspondence search gives us an initial configuration for our optimization process. In this step, the base shape is not deformed. We allow the user to control the trade-off between the base and animal shape deformation in our GUI. Here we show a low base shape deformation. Note how the horse is deformed. If the weight is set lower, the chair will be deformed to match the horse instead. The user can find a good trade-off interactively. The configuration after this step still results in an unpleasing zoomorphic shape. We minimize the configuration energy with continuous optimization. Here we show an example of the energy minimization process to find a good configuration. Once a desired configuration is reached, the shapes are merged together to form a zoomorphic shape. Our approach allows for several different types of user interactivity. In some cases, the user will want to alter the computed configuration to achieve a desired pose with semantic significance. Here the user changes the horse to be in a galloping pose. However, the user edit blocks the rider's view, which violates the volumetric design restriction. Our optimization adjusts the user's edit to achieve a configuration that satisfies the volumetric design restriction. This example shows the creation of an armadillo go-kart. The user can rigidly constrain the armadillo pose. Our approach can create different designs accordingly. We also allow the user to adjust the weighting of terms in the configuration energy. This example shows the creation of a horse chair. By controlling the weight associated with the visual saliency, our approach can create different horse chairs showing different portions of the horse. A rocking horse and a cow merges into a rocking cow. By allowing a larger deformation of the animal shape, our approach creates another rocking cow that is similar to this real-world design shown. Here we show more results: a bear mug, an octopus carousel, a phoenix plane, and a dolphin tricycle. Given a motorcycle and a jaguar, our approach creates a jaguar motorcycle similar to the real-world design. By using several animal objects as input, our approach can create a zoomorphic design with multiple merges, such as the dragon vase shown here. Finally, we show example scenes enriched by our zoomorphic shapes. An ordinary restaurant is turned into a zoomorphic-themed restaurant. A playground is turned into a more exciting zoomorphic playground. We have presented a computational approach for creating zoomorphic shapes. This is the end of our video. Thank you for watching.